Good afternoon, everyone. My name is Brianna Horton, and I am a Public Engagement Specialist here at Goddard Space Flight Center. Thank you for joining us for this month's Engage, featuring humanity's return to the moon. The Artemis I mission will launch later this year, and Goddard plays critical roles in this mission for the agency. Today, our panel will give you a little bit more insight into what that actually means. Before we begin, I just have a couple of housekeeping items to remind everyone. First, we will have a live question and answer session at the end of the panel. Please put your questions in the chat located on the right-hand side of the screen. Also, closed captioning is available for this Engage session, so please hover over the CC button at the bottom of the video and you'll be able to get closed captioning. Now I would like to turn it over to Mark Lupisella to kick off the panel. Mark?
Thank you, Bree. I'm coming through okay, yes? Just a quick confirmation from somebody. Yep, good. Thank you. Well, thanks for pulling this together. The Office of Communications here at Goddard, much appreciated, Bree, Laura, and others. This is kind of an exciting coincidence because we've got the Artemis I rollout today, this afternoon, which you'll see a slide on that. So we're excited to be sharing this material on this particular day. It's the beginning of a very exciting, few months and in years, frankly. So we're excited to be sharing this information with you all. So thanks for joining. We have a panel of three folks who are going to be talking about some specific things that we'll touch on just quickly in some intro slides. And so I was thinking I might intro them as I go through the intro slides. So, well, actually, I'll just say real quick. So we have Terry Herford, who's going to talk about IceCube. And then we have Kanekal, who's going to talk about an instrument we have called CuSP. And then we have Thanvi, who's going to be talking about our communication services that we perform at Goddard, which is a pretty extensive set of services, actually. So bear with me as I go very quickly through these intro slides, because we want to try to save some time for the panelists to talk in some depth and to possibly have some exchange if the audience may have questions. So we want to try to save some time there. So I think a lot of folks probably already know that Artemis I is not crewed. It's an uncrewed flight. However, it's obviously very important because we want to test out all the systems. And there are 10 CubeSats on board. These are smaller spacecraft that will be kicked off, and you'll hear about two of those in this conversation with Terry and Shri. So the launch here says no later or no earlier than May. Now that's actually moved into June recently, and the wet dress rehearsal that's coming up that we're rolling out for today will inform whether or not that gets delayed any further. Fingers crossed, and the wet dress rehearsal will go okay, and we won't have to worry too much about that. So here, I won't go through these details, but this is kind of just an overall flight representation. And maybe one thing to note, if you can make it out, is at the points A and B along the green line here. That's where we will be releasing the CubeSats. There'll be another one released later on, but that's the point in the process where we'll be releasing these CubeSats. And here's the stack in the vehicle assembly building, the VAB as it's called. We're just noting here that the CubeSats are right here in this OSA, the Orion stage adapter. Some more pics of the stack. This kind of gives you an idea of scale. You see some people here actually they're standing right where the OSA is. So that's right on the inside of that is where we have our CubeSats. And there's a picture of what we would expect the rollout to be looking like when that starts to happen today at 5. And so here, this slide and the next slide, these are lists of things that we do. So I'll just read through these kind of quickly, and some of it may come out in conversation more depth as either the people who are viewing this would like to hear or as a panelist want to try to discuss. But we've had a role in pre-mission trajectory analysis and emergency flight dynamic services. Veer's going to talk about this next bullet, comprehensive space communications and navigation support via the NSN the Near Space Network, then telemetry and tracking support during launch, reentry, and then number of points along the way, further out, actually past low Earth orbit. And then this terrestrial network connectivity between mission control, launch facilities, and agency space communications and network via NASCOM, a very old service that Goddard has been providing since, I think, pretty much since the beginning of NASA. Veer could probably say more about that. Then this independent assurance for safety, reliability, and security of the highest risk safety elements related to the software. So we've had a little bit of involvement there. And then emergency location services using an emergency beacon designed by the NASA Search and Rescue Office. So this is an office we have within our Exploration and Space Communications division, and they've been hard at work for many years on this service. And you'll see a little bubble about that in a second. So this slide, I won't really read through this, but this just mentions Lunar IceCube, which we'll hear more from Terry about, and then CubeSat to study solar particles, which will be something that Shri will talk more in depth about. And then these are sort of just the bubbles of areas that Goddard is involved in: space communication and navigation, space weather and heliophysics, which relates to CuSP, as you'll hear more about, lunar and planetary science. There's actually quite a lot that we do there. And spacecraft instrument technology development, then search and rescue. You heard you mentioned that just a second ago. And then Wallop's flight facility, which is part of Goddard, has a very agile launch and rapid prototype capability that we're bringing to bear in various ways. And then more generally, we work on a wide variety of things in exploration systems and in-space services. So I think with that intro, if we're ready to press on, I'll ask Veer. I'll ask Veer to just tell us a little bit about his role at Goddard, and then we'll dig into some of the communication details after that.
Thank you, Mark. Hope everybody's having a good day, and it's a great privilege to be here and in this engaged session. And beyond that, it's a bigger privilege to be part of the Artemis I mission, which is one day going to take the humans back to the moon, as we did decades ago. So pretty exciting time. As Mark mentioned, the rollout happens today. So my name is Veer Thanvi. I'm Deputy Program Manager for Exploration and Space Communication Division here at Goddard. I am also acting project manager for Near Space Network, which Mark mentioned earlier. Near Space Network, if you want to find out more, I can just summarize in maybe one-liner as it's basically the network serving all the missions which are in near space, defined as from surface of Earth up to 2 million kilometers out. So fulfilling missions needs for communication and navigation services in that orbital regime is what Near Space Network does.
Thank you, Veer. So do you want to try to say a little bit more about the Common Nav support that Goddard is providing specifically for Artemis I?
Yes, absolutely. Great question, Mark. I should be kicking this off by saying it is very proud to be a Goddard team member that end up supporting Artemis even before it gets to the pad, and also when it goes off the pad and lands back in the ocean. All the way throughout the life cycle of Artemis, Goddard has a very important and critical role, especially if you look at the Near Space Network. If you look at all the phases of the pre-launch, where it is on the pad, trying to communicate, going into the ascent, going into the LEOP ops, going into the translunar, and then from lunar to trans-Earth and back to re-entry, landing in the ocean, all of those phases of Artemis are supported by what we call the network. And the reason and everything that goes in there is communication, which means at any given time, Artemis always has a way to phone home. It is continuously connected. And navigation, which means at any given time, Artemis knows where it is, and we know where Artemis is. And that's the way we provide a pretty comprehensive service in terms of supporting the entire mission through its operational phase, However, I would start by saying Goddard has near space network, which gets involved very early in every phase of the mission. As soon as we know that the agency or the nation is ready to go to the moon, we know there will be a mission that goes there. Right at that point, NSN gets involved to integrate that mission, to get our network ready such that all the combination configurations, everything that is needed is not only implemented, but tested, verified, validated over and over, such that when time comes to provide an operational service, we are ready to go. So during the pre-launch, launch, and ascent phase, we will be providing command and telemetry services to like Orion and SLS, and we actually have built new ground stations out in Bermuda, right? Some people might know near Kennedy Space Center. That was built only for this purpose. After you go over the range of providing a direct-to-Earth service where you can't just rely on a ground antenna, we hand it over to a space relay service. There is a whole fleet of geo relay networks that Near Space Network has. That's the one TDRS that takes over the communication at that point. And we have many supporting elements that we coordinate with as a network. We work with flight dynamics for orbital dynamics needs. We work with NASCOM, as Mark mentioned earlier, for our terrestrial comm needs. We have the search and rescue. We have organizations within Goddard, outside of Goddard, and even outside of the agency that we all collaborate with to make sure a comprehensive service, secure and reliable, is provided to the Artemis mission.
Thanks, Veer. That's interesting. That conveys the sort of the breadth of organizations and the breadth of services that have to get involved in this kind of thing. And so somewhat related to that, thinking down the road, do you what would you envision for future Artemis support? And will it be notably different? Is there anything that would really stand out as being particularly different when crew is on board?
Yeah, so that's a great question, Mark, right? I mean, Near Space Network even today supports what we call human spaceflight missions. We have astronauts who go to the International Space Station, and even the cargo that goes to International Space Station. We support all of those missions, human spaceflight missions today. Right? What is different with Artemis I? So that part for us is not different. But what is different for Artemis I is we now have more rigor on those processes because we know one day there will be a human on one of these Artemis missions going to the moon, right? So we utilize our support, we utilize our experience that we have gained by supporting the missions going, crewed and uncrewed missions going to International Space Station. And we identified the need of having new ground stations to support Artemis I. That's how we see that is a mix of leveraging what we know, doing a little more, knowing that we are going farther in this space, and we will go with humans in this space. So when Near Space Network looks at the Artemis I mission, we look at it as if it is a human-rated mission, and it actually is a human-rated mission. So even though if it is a test flight, we will treat it as if it has humans on board. So that's the additional rigor we put on it. That's the additional analysis we put on it. We go more in depth to analyze every possible scenario to make sure the comm and nav services are always up and connected and running. They're more accurate than they need to be, more precise than they need to be, and always ready for any type of contingency or non-nominal or critical support, knowing those scenarios may or may not come up, right? So that's our role going forward as we support Artemis I, and for future Artemis generations, as you brought up. If nothing else, the rigor increases even higher because we are going to have more and more assets. We're going to have more and more humans, right? I mean, going with Artemis I, sure, we have a lot of CubeSats. We want to go up there and explore that spatial regime, which is not as well explored as Earth is today. So that allows us to look at more and more nuances in that area so we can learn more before we send the human up there. Near Space Network does the same thing to say, we are learning more, we are going farther, we are going to not a new place, but we are going to a place where we haven't been there for a long time. Let's make sure we have all the right communication and navigation services up and running for the mission.
Yes, thank you. That's a good point about the rigor, the level of rigor associated with Artemis I, even though it's uncrewed. Part of the point, well, a huge part of the point of Artemis I is, of course, to really just test as much as we possibly can. So there's a ton of rigor just associated right now with Artemis I, even though it's uncrewed, so that we can make sure that those future missions go smoothly, whether it's comm, nav, or anything else for that matter. Okay, so moving on, we have Terry Herford, who has been heavily involved in Lunar IceCube, and I've also been a bit involved in Lunar IceCube for a number of years. It's one of the CubeSats that's flying on Artemis I, and we'll be rolling out hopefully today. We'll be right near the top of the vehicle in that OSA, that Orion stage adapter. So Terry, did you want to say a little bit about your role in IceCube, or even more broadly, anything regarding Artemis?
Yeah, thank you, Mark. My role at Goddard is a planetary scientist. I study the natural satellites of many of the planets in our solar system, mostly outer solar system satellites like Europa and Enceladus. I look at the geology on these surfaces and try to figure out how that geology formed, and also look at processes in the interior that are converting tidal energy into heat. And the moon is a very special place in that it is tidally active. Also, and as a new target, to go back to with human exploration, we really want to know more about its surface. And so I got involved with the Lunar IceCube project, and specifically the instrument payload on that CubeSat, which is going to be looking for the signs of water on the surface and kind of map it in the polar regions and get a better understanding of water and the water cycle on the moon. And I'm the instrument scientist for that instrument. And so my role is really to look, as we developed the instrument and we had engineering challenges, to overcome those challenges and make sure that the science was still preserved. And then when we put the instrument into the CubeSat, make sure that the design of the CubeSat still allowed us to do the science that we wanted to complete with the instrument.
Sorry about that. I got tiny little delays on my computer that's working very hard for us. So yeah, thanks, Terry. And just mention real quick, one of those challenges that we faced with a CubeSat is the thermal challenges, right? Got to keep the instrument cold, but the spacecraft's extremely small. And even though you might think a small spacecraft should be easier perhaps than the larger spacecraft, and in many ways it is, this presented some unique thermal challenges that we really had to work hard on. In fact, I'll just mention briefly, Cliff Brambora, who's the lead instrument engineer, just did a ton of work and really did a great job getting this instrument to a point where we could get the temperatures where they have to be. So Terry, did you want to say a little bit more, say perhaps about the comparison of previous water discoveries on the moon, and then maybe what IceCube is intended to do a little bit differently, or what additional knowledge may be brought to bear by the measurements from IceCube?
Yeah, so we have a lot of indication that there is water on the moon from other types of instruments. We've been able to map hydrogen in the subsurface near the surface of the moon, and it kind of gives us a hint of where water might be. There was an Indian spacecraft that carried the Moon Mineral Mapper instrument that showed that there was an absorption feature around 3 microns, which is indicative of water, but it didn't show the full spectrum out there. So we didn't know whether or not it was a hydrated mineral or actual water ice itself. So the Birch's instrument inside Lunar IceCube is a near infrared spectrometer that covers that full 3 micron region, so we'll be able to see that absorption feature that the M-cubed instrument saw, but we're going to actually be able to fully characterize the absorption feature and really tell whether it's hydrated minerals or water ice that we're seeing from the instrument. In addition, because of its unique orbit, the Lunar IceCube with the Birch's near IR spectrometer is going to cover the same terrain at different phase angles of the sun. So throughout the day, we're going to be able to see if this 3-micron feature changes. You might expect that as the day gets warmer and we go toward noontime temperatures, water might migrate away from the hotter temperatures on the surface, and that might change the feature. So we're going to actually be able to look for the water and look to see how it changes throughout the solar cycle on the moon.
And that kind of relates to another question, which is how specifically can we imagine this data helping future human missions, say, to the surface? Any thoughts about that?
Right, since human exploration is the goal, taking lots of water to the moon is expensive. It takes a lot of money to launch things up into space and get them to the moon to begin with. But if we can find these resources on the moon and utilize them in place, then that doesn't mean that allows us not to carry them with us. So if we can find deposits of water and send crewed missions to those locations, then we can exploit the water there, and water can be used for the crews themselves. It can also be broken down into oxygen and hydrogen, which is a great fuel source for getting back off the moon. So water is a very important resource that we need to identify, and so we need to know where it is and then how it changes throughout the daily cycle on the moon.
Yes, thanks. Yeah, I think that that added point about how it changes over time is something that IceCube's going to really be able to help with, and there will be other missions as well that will be able to help with this, and so it'll be an aggregating of a lot of data from a lot of different missions, including missions in the past as well, to really help understand the water story on the moon for all its relevance to human exploration. Let's go ahead and move on to Shri, who will talk to us about the importance of an instrument that he's been involved in for space weather and heliophysics, and that's something called CuSP, CubeSat, for solar particles, and I think it's maybe worth noting that we don't often think too much about the space weather question. Certainly NASA thinks a lot about it, but it's not always entirely obvious that what the sun is doing can be extremely important for safe human missions, particularly as we go to Mars. So, Shri, did you want to say a little bit about your role at Goddard first, and then we'll get into some details?
Yeah, sure. Thank you, Mark. And as Veer was saying, it's really a privilege to be on this panel. Yes, CuSP is one of the CubeSats, just like IceSat, which will fly on Artemis, and will be dropped off somewhere in the middle on the way to Moon, which Mark showed in his intro slides. It's a CubeSat, which we call a 6U CubeSat, which is 1U is a measure that's 10 by 10 by 10 centimeters. So this small satellite, which is the size of 2 loaves of bread put together, has 3 instruments on it. One which measures the local magnetic field. Some of you may know that even in the interplanetary space, that is space between the sun and any of the planets, we have a magnetic field that emanates from the sun, which is the source of that magnetic field. So we have an instrument to measure that. And we have another instrument called CIS, which measures lower energy particles. And then there is the instrument that I led called MERIT, which measures much higher energy particles. Now, these particles are coming from mainly from the sun, but also from everywhere in the galaxy. Those particles are called galactic cosmic rays. The particles that come from sun are called solar energetic particles. And the importance of having the magnetic field is that the magnetic field actually sort of guides these particles. So the particles stream along the direction of magnetic field. And these particles range in energy from very low energy. I can give some physical units, but that doesn't matter so much here, to a very large, very high energy. And these energetic particles pose a significant space weather hazard. Why is that? Because these very energetic particles can penetrate your satellites, the space suits which astronauts would wear and when they are going for an extravehicular activity, for example. And as we all know, radiation is harmful to us. It causes cancer, for example. So it's important from NASA's perspective to be able to characterize this radiation environment. Since we, as an agency, are committed to take people, I should say, to Mars, and that long flight from Earth first to Moon, which is Artemis II, we want to have the so-called lunar gateway, which is going to be a gateway for Mars. And when a long flight from even, let's say, from Moon, which is pretty close to Earth, and all the way to Mars, you're traveling in a spacecraft and which is exposed to these extreme events from the sun, which suddenly spews out bursts of these energetic particles, and which can, like I said, penetrate an astronaut suit. If you are enclosed in a nice human module, you're probably safer. But there are other effects, like it could affect electronics, it could affect your navigation systems, it could screw up your ability to communicate, which would, of course, distress Veer with all his hard work, and it could pose a significant danger. So it's important for us to characterize these energetic particles, and the instrument that we built at Goddard and delivered to the PI, so-called the Principal Investigator Institution, which is Southwest Research Institute, which put together the satellite. So we built this energetic particle instrument at Goddard, and that was my main role in this mission.
Thank you, Shri. That was a great overview. Are you able to say something about the final location of the spacecraft? I mean, people may not realize exactly where this is headed, but what's the ideal ending up spot for this spacecraft?
So in principle, there is, we'll be dropped off somewhere between, that all depends on the final orbit and such. So in principle, we are not that sensitive to where exactly we will be dropped off, because we want to measure these particulate environment, the magnetic fields in any point between the sun and the Earth. So in what we generally call as the interplanetary space. And these particles, for example, can be driven by something called coronal mass ejections, which is huge blobs of plasma spewed out by the sun. And just to give you a scale size, these are hundreds, if not thousands of times larger than the Earth itself. So it really doesn't matter where we are in that space. Recent, discoveries by spacecraft have shown that these SCPs, or the solar energetic particles, span a large extent of solar longitude, just similar to, for example, Earth longitude. So if there is a major event, the chances are very high that no matter where exactly we are located, we would be able to measure them and characterize them. Of course, it's possible that we may be slightly off. We may not get the peak intensity, but let's say we measure some particle intensity which is pretty high, and we know from other measurements that wasn't the peak intensity. That should be actually also pretty useful, because even if we are not off the exact, we are not in the line of sight of the gun, so to speak, it's not a rifle, but a shotgun. So it's the particles are coming everywhere. Even if you're not facing the shotgun directly, you can still get the intense particle bombardment. So it's, to some extent, we are not very sensitive to where exactly we will be dropped off on the way to the moon.
Yes, thank you. Good point of interesting distinction between what many of the other CubeSats are facing versus what your spacecraft can tolerate. In the case of IceCube, of course, with trajectory, lots. In fact, I'll mention a couple of people like Goddard, Dave Folta, and Sun Diaz have been working a lot on flight dynamics for IceCube, and it's quite a process. There's a lot that goes into it. Every time the launch changes, right? There's a whole bunch of work that's got to get done to reevaluate trajectories, et cetera. But I think in your case, it's not nearly as important, perhaps. To nail all that down, because your final location, you've got a lot of play in where you could end up, and that's nice. I mean, you get the free, more or less free ride on Artemis I on SLS, and you can end up, almost anywhere in space where you can make these detections. So it's a really nice win-win combination, I think.
Yes, in NASA speak, we can say that our requirements are minimal.
Right, indeed.
So when we propose a mission, when we are asked, okay, what do you guys need? Where do you have to be looking? How much power do you need? And if you go far away, can the communications be established? So from all those points of view, we are very easy on these requirements. So we just need to be looking towards the sun. Anywhere in space is okay. If it's not too far away for Veer to contact us, fantastic. That's it. So, and we can still, none of that affects our science or our characterization of the space weather.
And thinking ahead, and you already kind of mentioned, the relevance of this as humans are traveling in space and maybe going out to Mars, but do you want to expand a little bit on how this spacecraft and its measurements and actually related data, if you want to comment on that, because I'm sure you're familiar with a lot of data that's related to what your mission is doing. How do you see that playing into ensuring mission success in the future when humans are going to the moon and really beyond to Mars?
Yeah, so first of all, it's important to mention that these CubeSats, which are a sort of a recent technology, are a cheap way, inexpensive way to get to space. And the instruments we build on the spacecraft, the spacecraft is very compact, less than a few kilos. So the instruments are also very compact. In the past, when you flew these spacecraft and the instruments that measures exactly what we are measuring, cost much more. They were much massive, and even to launch those. So, for example, there's this so-called Lagrangian point, which is where the gravity between the sun and the Earth cancel out, and that's used to monitor interplanetary space weather, if you will, because you can park a satellite there and it'll just stay there because it's being pulled on one direction by the sun, it's being pulled on another direction by the Earth, and these pulls equally cancel out, so it's just staying there. And that's what we call a space weather, like a space monitor. It's very, very useful. And there have been many spacecraft that NASA has used. For example, ACE is one of them. So constantly we are monitoring. That's a very good thing. But now a spacecraft like ACE to build, to fly, is expensive. It's not a trivial thing. It would require a lot of oversight from a lot of people, from the safety perspective, from the build perspective, from the expense perspective. You spend hundreds of millions of taxpayers' dollars. Are we getting the right return on investment, and all that sort of a thing. Whereas a CubeSat would cost you a few $1 million, nothing more. And if it goes wrong, fine, no problem, we can put another one. Has a quick turnaround, and the important thing is all this has been enabled by advances in technology. So the instrument that I was responsible for this weighs less than 1 kilo, for example, a few hundred grams, okay? It does the same thing. I was involved in a major NASA mission called Van Allen probes, which studied radiation around the Earth. We had an instrument there in which also I was heavily involved that cost something like 20 million, okay, and weighed 18 kilos. So you can see the advantage of CubeSats. They provide another big thing is everybody since James Van Allen himself, who discovered the radiation belts, have talked about importance of multi-point measurements. You know, if you just have one measurement between the sun and Earth, there's a vast space, whereas you can throw out a whole bunch of CubeSats and you have 10 measurements from 10 different spots, and you can synthesize them together and get a picture, if you will, almost like an image of how particle intensities are coming at you. And those kinds of things are enabled by CubeSats. So I would say this is a very complementary thing to big missions, which of course are still needed because they can, you know, they will, for example, ACE has stayed at Lagrangian point for years now, whereas a CubeSat, being small, cannot itself protect against the radiation which it's measuring. So there is, you know, it provides, the CubeSats provide a complementary niche, if you will. So I think that's what is the importance of doing measurements on CubeSats.
And looking forward, presumably we can get all these multi-point measurements at much reduced cost because we've got this sort of new approach, newish with CubeSats. And by the way, thank you for mentioning some details about CubeSats, you know, like how big they are and how big these particular CubeSats are, being 6U. We didn't touch on that, and that's a good thing to point out. The IceCube instrument's also quite small and low in weight, and Terry can talk more about that if he wants. Your point about multi-point measurements is a nice segue to a question for all of you, actually. I think, Terry, maybe I'll point this at you first, and this is the question of sort of complementary measurements with other missions, particularly maybe other Artemis I CubeSat missions. Do you want to say anything about the potential for leveraging data from some of these other missions to maybe complement what IceCube is doing, or to just contribute to a larger data set that'll be useful?
Yeah, so Lunar IceCube is looking for water, but so are some of the other CubeSats that are going to the moon, such as Lunar Flashlight. And it's going to use a more, I think, an active laser source to look for reflections of ice in the polar regions. And so because there's multiple ways at looking for water, these CubeSats kind of work synergistically to find the evidence for water on the surface. And then they can also add to the data that we have from past missions and even future missions with the CLIPS program that's sending payloads on commercial satellites that are landing on the moon itself to get ground truth. Then we can link that ground truth measurement to the orbital measurements that we're taking with the CubeSats. And then by that ground truth, we can extend our measurements to understand what it means for other places where we're not visiting yet. So all these things, the more data we can get, the better to get a global picture of what's going on the moon. And that's exciting.
Yeah, yes, and CubeSats offer this opportunity in part, and if others want to comment, please do, in part because of the standardization of the form factor, right? It's, you know, these blocks, these cubes essentially, and there's been a kind of whole, I guess I'll use the word industry, a kind of mini industry that's been growing up now with this form factor, which is really nice because lots of players can get in and do things inexpensively and contribute, like you guys were just saying, to this larger data set with different approaches and low cost. So we get to do lots of experiments, get lots of data in the process, get more players and people into the system, including lots of people from universities, which we should mention too. IceCube is led by Morehead State University, and we've been working very closely with them, but they've been doing a great job leading what is actually ultimately a pretty complex mission because of being on SLS, being on Artemis I, and because of the lunar flight dynamics. In fact, that question about the launch vehicle is one of the questions that's coming up, and maybe we'll touch on that briefly. Thinking we might. Maybe we'll do that now. Should I ask Bree or anyone else?
Just briefly mention something regarding CubeSats. CubeSats, indeed, they have many advantages, as has been mentioned multi-point. And one of the, however, disadvantage is because of their small size, they cannot communicate from large distances or send down large amounts of data from close distances. So I'm sure maybe Veer has something to say about this. There's a lot of work going on to increase the data throughput between something such a small thing as a CubeSat. And that's, by the way, one of the advantages like a big major mission would have. They have a huge antenna, they have a lot of power, they can turn the antenna towards the Earth and stream down gigabits of data. Whereas that's a super luxury for a CubeSat. But there are innovations going on, and I don't know, Veer perhaps he's certainly better qualified than I to discuss this.
That's a great point, Shri. I agree with you, right? That there are pros and cons of looking at the things when you have big instruments continuously sending a pretty stable stream of data. Whereas compared to when you take a look at CubeSat that can collect a lot of things in a short period of time and burst it down, and then it kind of slows down, right? So the way the network would mitigate, or I would say be prepared to support both ends, right, is as we do today, we got variety of apertures on the ground. We can go from as small as a 3 to 5 meter antenna. We go as large as 20, 34 meter antennas. Right, and that's how the more you cover the landscape on the Earth, then you support more and more coverage and more distribution between the apertures and the size of the missions all around the globe for direct to Earth services. Similarly, what we are trying to do is when you go up in the space, if you are anywhere geo or below, we got the geo relays, the TDRSs, right? That's what takes care of all the space relay services. We as an agency are going to be looking on how we can enable something like that when we are on the moon. Right? So we want to cover the entire region as far as we can go to make sure we can talk to you directly from Earth, or we can talk to you through a relay. That would enable more communications and more data coming down, which obviously leads the entire humanity to more of a scientific discovery, economic benefits, right? And going back to the moon, it inspires a whole new generation of explorers, in my opinion. Yeah. Right? If somebody asks us today, like, what are you most excited about going back to moon? Right? Yeah, so it's like you go to Disney in 1940s, it was still Disney, pretty exciting, right? You go to Disney today, you find new rides, you learn new things. Okay, we're going back to the same place after a few decades, but we have more technology. We have more scientific discoveries to make. We have more things to explore, right? So it always inspires a new generation of explorers to say, what else is out there? Are we alone? And what the environment looks like? What can sun do to us? Can we find water, right? And can we sustain human life? So we are not necessarily going to moon to colonize it. We are going there as to learn more, explore more, and also benefit ourselves to say, can we make that a pit stop, sustain life as we head our way to the Mars, right? So, but thank you for raising the point that there are definitely evolving communication and navigation needs.
Yeah, thanks. Thanks, Shri and Veer, and well said, Veer, on that inspiring next generations piece of it. That's actually one of the questions we were heading for. I'm doing a quick time check here, so we're coming up on 1:47. So we got some questions coming in, and Veer, since we were on you, maybe we'll very quickly ask this question, which had to do with search and rescue, but I do want to make sure we leave some time to come back to that larger question about what are we looking forward to? What's going to be inspiring us, yourselves individually, as well as collectively? I'd like to come back to that and get some more input on that. But one of the questions that came up here, Veer, was having to do with search and rescue. And I'll just read it word for word here. You mentioned search and rescue. You normally think of that here on Earth to find people who are missing. How will that work in space and on the moon?
Yeah, I think that's a great question, right? So when we think about search and rescue as it relates to Artemis I, I see that in two ways, right? Number one, obviously, as everybody knows, when the astronauts come back to the re-entry and get into the ocean, you gotta know if something goes wrong. We hope everything goes right. We plan for everything right. If something goes wrong and they were to eject somewhere else, the search and rescue beacon is what enables us to go find them. So that's the Earth part that everybody's familiar with. How would it work in space, right? When we are walking on the Earth, we have GPS. And that's why I always say that the communication and navigation part as we go to the moon is very important. When you are walking around the moon, there is no GPS satellite. When you are walking around the moon, there is no way for you to know. Here you can watch the evening news and you will know it's going to snow tomorrow. When you are on the moon, you have no idea what event is going to take place which can impact an astronaut. So you need to have sensors, you need to have navigation, you need to have a network that tells you at all time where you are. So linking it back to search and rescue, when an astronaut goes out on the surface of the moon and he or she needs help, there is a beacon that they can initiate, which can come back to Earth. We can also be broadcasted to other assets on the moon that can immediately become available to help whoever is in the need. And that's how the search and rescue function would work in the space.
Thank you. There's a bunch of good questions coming in here, so I'm scanning through and I'm tempted to kind of just, because they're all good, I'm going to just take the next one I see here, and I'm thinking maybe, Terry, if you want to jump in on this first, and then I don't know, Shri, you may have something to say about this as well, but this is a question about the challenges we face by being integrated into, say, this very big rocket that, you know, has quote unquote primary purposes, right, which is to test Orion, et cetera, and we're going on as secondary. So anyway, I'll just read the question straight away. What kinds of obstacles are the CubeSats experiencing as a result of being integrated into the launch vehicle for so long before the launch, right? So this is an interesting question, and I know we've on IceCube we've faced a little challenge there. So Terry, did you want to say something quick about that?
Yes, I think we've been integrated into the Orion, into that ring underneath the Orion capsule, and I don't know how well the environment is being controlled. And so with our optical instruments, you do have to worry about contamination of the mirrors and such that would degrade the amount of science that we can do and the type of science we can do. Fortunately, on the Birch's instrument, we do have a door on the front of the instrument that we can close and keeps particles from easily getting into the instrument. We do have to worry about water and such kind of getting in there. And once you launch, that water will want to freeze out and become ices. But the long period of time between going from our ejection site from that ring to the moon will probably allow a lot of those volatiles to then become ices to become gases again and escape the instrument. And then plus the thermal issues that we've had on small satellites means that it's going to be fairly warm inside the satellite too, which will help kind of volatilize any ices and get them out of the system. So I don't think it's a huge challenge for us, but it is something we have to think about in that if we integrate too soon, just how does the system degrade over time? And I do know that the fuel source, we're using a very exciting new propulsion system, which uses iodine. It ionizes it and shoots it out a thruster, which gives us a very small pulse of energy thrust. And over a long period of time, that low thrust will allow us to change our orbit to become captured around the moon. And that fuel source over time can degrade, so we don't quite have as much fuel as we had when we first fueled up at the beginning. So the longer we wait, it starts to impact our reserves a little bit. But we made sure to hold enough fuel to account for a slippage in the launch window.
And just recently on IceCube, Cliff Brambora wrote up a little operational scenario where we could actually accelerate a little bit what Terry was saying about heating things up a bit, right? Basically pointing in such a way that there'll be a little bit, really essentially just pointing the face of the spacecraft in question to help with the instrument, which has got this neat little deployable radiator on it. Actually just sort of flips up to give it extra radiating capacity. But anyway, in this particular scenario, to help with it, we're thinking, hey, we can probably point that at the sun, increase the heating a little bit, and then accelerate the process that Terry was talking about. So we're in the process of actually evaluating that. And as of right now, it looks very feasible to do that. Shri, did you want to mention something about this, the kind of challenges faced by a long-time integration? And we're going on 7 minutes here. Bree or Laura, anybody else, if you want to stop us and redirect, and I don't know what kind of time we have to have at the end here, but we'll just keep cranking unless you stop us.
Yeah, I can just add one little thing. It's just along the lines of what Terry just said. In this case, I'm referring to the onboard power, which is a battery. Until the solar panels deploy, we are dependent on the battery. So if the battery is fully charged, everything's fine. But from the point of integration, from that point on, when we deliver and we do have no access to the CubeSat, and to the point when it's integrated and to the point when it's actually released, if there is not enough power in the battery remaining, then the mission, that's a single point failure for the mission. So until we need to have some power, at least until the solar panels deploy. So that's one of the challenges also.
Yes, and actually at the Cape, despite the fact that it's down in Florida, it actually can get quite cold. There can be some weather patterns that cause some cold temperatures. In fact, we hit some below freezing temperatures a little while back, and that actually made us a little bit more concerned about some of the contamination stuff that Terry was mentioning. I see another question here that I think would be for Shri. I guess there's going to be these mannequins, right? They're going to have some sensors for radiation purposes. I don't know what your familiarity is with that, or whether or not you know anything about how that might complement the CuSP data, or vice versa. Do you have anything to say about that?
I don't know about these radiation monitors, but the instruments on CuSP. So many of these radiation monitors, I'm aware of one type of them called dosimeters. They measure total dose, total radiation impact, if you will. But what we are doing on CuSP is actually measure the full, what we call the spectrum. That is how many particles are there at a given energy. So we can say there are 100 particles of X energy, 200 particles of Y energy, 300 particles of Z energy. So we can then take that's additional information to just saying, oh, there's just more 500 total particles above certain energy, which is what these dosimeters do, which is important. But both from a science and the space weather type understanding, it's important to know the full spectrum of the way these particles are distributed in energy, in the direction at which they are coming, and all that stuff. So this instrument is capable of doing all that.
Yeah, great. Thank you. So we're heading towards the end. There is this one question real quick. I'll make take a shot at it. Will there be additional opportunities for CubeSats as secondary payloads on future Artemis missions? My understanding is that that's the hope. This mission, this Artemis I mission, is probably going to inform the extent to which that's going to happen in the future, what kind of things might change, et cetera. So yeah, there should be plenty of opportunity for this in the future. Where, when, and how exactly, I think that's to be determined. So in the last few minutes, we heard Veer talk about some of his sort of inspirational view of things and how this can inspire future science, future generations, et cetera. Terry or Shri, do either of you want to say, well, I guess I'll just ask Shri first, since you were just talking, Shri. In a couple sentences, what are you excited about regarding your mission, or just in general?
Right. In particular, I'll say in general about CubeSats. Okay. So the CubeSats also provide a big space mission takes years, if not a decade, from the start to finish. Whereas a CubeSat mission takes just a couple of years, maybe 3 years at max. Which means a young person starting out as a scientist, as an engineer, as a space vehicle manager, any of these roles, they can get training. And the CubeSat, in fact, the very first CubeSat I was involved was from when I was at Colorado, at the University of Colorado. We built the CubeSat was called Colorado Space Weather Explorer or something like that. And that was completely built by students with oversight from experienced engineers and people helping them along. So that was all done, and it was a very successful CubeSat, made many publications, peer-reviewed journal publications. So I think that's the inspirational thing for young people. They can go from start to finish for a full space type mission.
Thank you. And Terry, real quick, what are you looking forward to?
I would echo that, just the ability to do a lot of science in a short period of time, and to see and get the experience of developing instruments and seeing the life cycle of a mission. I'm on the Europa Clipper mission, which I think was selected back in like 2017. It's not launching until the later 2020s, and won't get to Europa until the 2032 timeframe. So most of my career has passed with that mission, but to actually get the experience of developing an instrument, building an instrument, getting it on orbit, and getting data from it, the CubeSat and Lunar IceCube has really fulfilled that and given me a much broader experience than the very slow chugging Clipper, which, I mean, because it's going to the outer solar system, it naturally takes a lot longer. And so because we can do this a little bit more rapidly and get back a lot of good quality data that can then inform our other instruments and other bigger missions that we want to send, CubeSats have a really exciting place in the portfolio of NASA missions.
Thank you, Terry. I see Bree is back and is going to take us out. And a big thanks again. Thanks to the three of you. Thanks to the communications office. Greatly appreciate it. I know there's a lot of work that goes into putting these things together, and Travis doing things behind the scenes. Much appreciated. Thanks. I hand it off to you, Bree.
Thank you. Thank you, everyone, for being on the panel today. It was extremely informative, and we're all looking forward to the Artemis I mission launching later this year. I just want to say that this is our last totally virtual Engage that we will be having. The next month in April, we will be doing a hybrid version, so you can come see us in person or join us online. So thank you, guys. Have a great day.
Thank you.
Thanks.
Thank
Bye.
you.
Bye.